Hey everyone, welcome back to Data and Donuts. My name is Aaron. I'm here with my friend and colleague, Terrence Willett. And today we're going to talk about inferential statistics. But before we get into that today, I will have Terrence tell us a little bit about himself.
Hi, I'm Terrence Willett. I'm a Dean of Research Planning and Institutional Effectiveness at Cabrillo College and a Senior Consulting Researcher with the RP Group on projects such as multiple measures and some other projects, including EOPS and evaluation and some other items that we have going on, including strategic enrollment management. So all kinds of good stuff.
Excellent. And so, as we mentioned earlier, today we're going to talk about inferential statistics. So what are inferential statistics?
Well, there's the textbook definition y'all can look up in Wikipedia, and then there's what I'll say. I'll start more on the traditional side. You use them to infer information about a population from a sample. That's the classic thing. And you've got your hypothesis tests and parameter estimates. So an example of hypothesis testing would be, does tutoring work? Yes or no. Whereas an example of estimating parameters would be by how much does tutoring increase success rates? And you're trying to get more at an effect size. And it touches on differences between populations and samples. And so in the context of institutional research, one of the very first things that you learn, and I realized this on day one, and I sit down with the data and I say, oh my gosh, I have population data. Most of my inferential statistics are useless because you've got your population for the most part. So we'll touch on that a little later about, well, how and where can you use inferential statistics in institutional research. But a related thought with inferential statistics is you're really trying to get at causality. Quite often, does a particular program cause students to do better or not? And one of the more fun philosophical road trips to take is from the idea of counterfactuals, in part from Dr. Lewis. He had a 1973 book called The Counterfactual. And for those of you who are a little younger, you might think of this as the multiverse. So, you think about if you could observe how students did in the universe where they did not receive tutoring versus how did they do in the universe where they did receive tutoring, then you could compare the two and determine the effect. And so some techniques have that philosophical basis where you define and then try to measure the counterfactual alternate universe where the students did not engage in that program or service.
Excellent. And so how have you seen, you kind of got to that a little bit, but how have you seen inferential statistics used in higher education?
Yeah, I think the big one is the parameter estimates more than the hypothesis testing in general. A lot of what's referred to as predictive analytics. For example, sometimes enrollment projections are a big deal, and then you're trying to infer the future from the past, which of late is extremely difficult because all the traditional predictors don't work anymore. You can't use some of the like unemployment rates. They don't have the same effect on. They don't have the same predictive power as they used to. A couple of examples. One is tutoring. That's one that we've done. And because you, on a causality side, you can't truly observe an alternate universe yet, it's coming. Another approach would be to have an experiment, randomly assign students to do tutoring or not receive tutoring. Experiments of keeping students from accessing services or forcing students to access services are generally problematic. It's hard to do experiments, and so you tend to use quasi-experimental designs, using multivariate analysis like a logistic regression or propensity score model. There's a lot of machine learning techniques that come out of computer science They tend to have a different philosophical background. They tend to not be strictly classified as statistics at all, let alone inferential statistics. And rather than a hypothesis testing, trying to determine what's going on in a population, a lot of it's grounded in information theory, trying to do pattern recognition, signal processing, and so on. And you have techniques like one of my favorite classification regression trees, but you got a boatload of other, support vector machines and neural networks. And it's interesting because they're more focused on just trying to describe the data and maybe also using it for predicting, but its theory tends to be more theory free. You're not really grounded in some theory. You're just wondering who's going to do what. And I don't care about the theory. I'm just trying to have an applied setting where I want to know, does this service work? Are the students going to respond to this marketing approach? Whereas in the traditional inferential statistics, it's very social sciencey. Tends, what is your theory of action, like student engagement theory, and so on. Another example where we relied more heavily on machine learning techniques to do predictions or inferential statistics, or the what-if scenario, was in the multiple measures project, where we used primarily decision trees in the mature stage of the project to answer the what if question. What if students who had previously been placed in below transfer coursework, what if they had been able to start off in transfer level coursework, and what were their success rates have been? At the beginning of the project, we did use a variety of techniques. We did look at logistic regression and support vector machines and gradient basis models and all sorts of different things to try to find what was the best approach, both that would be accurate but then also understandable and be actionable and usable. And so that is an example where we use decision trees to help out with that particular project. One last example I'll give is the one time in my career I got to do an experiment over 20 years ago, and I used a neural network actually to predict whether or not a group of students would persist from one semester to the next. And then I took a random sample of those predicted not to persist, 100 students, gave the names to our counselors, and then they called the students up and said, hey, are you planning on re-enrolling next semester? Is there anything we can do to help? And the students who received that intervention were almost twice as likely to re-enroll as those who didn't get that intervention. So, and then the statistics on that were pretty easy. It's just a t-test. In that particular case, you're just using the very most simplest statistics rather than doing something fancy, even though I used something fancy in order to draw the target sample. Unfortunately, it's a lot of work, and we didn't necessarily keep it going. But having an experiment and then being able to use very simple statistics, there's always that fun quote from Ernest Rutherford, which I don't really know if he said this, but the internet says he does. If your result needs a statistician, then you should design a better experiment. So that's always important, that fancy stats can't make up for bad design or bad data, right?
That's funny. That's hilarious. I think I should get that put on my wall in my office. Hopefully it'll cut down on the difficult questions and quasi experiments. So when thinking about that, what are the considerations one should make, when using inferential statistics?
Yeah, I think I just touched on one of the big ones is you gotta have the right data. If you've got bad data and you can analyze them correctly, and you'll come up to a bad conclusion and take a wrong action. So your data quality and your data prep and how you structure the data, 80, 90, 95% of your project, and the most important part. So no amount of fancy stats will fix that. And there's limits if you were dealing with a quasi-experimental design, like you're trying to predict what's the effect of a particular intervention, be it tutoring, learning communities, a student service program, new pedagogy. If you don't have random assignment and the students have agency or choice in which condition they're in, it's hard to completely eliminate self-selection bias, even using the fanciest stats or machine learning techniques. So you always have to keep that caveat in mind that what you'll get out of these techniques are suggestive, uh, but you want to hold a little shy of saying with absolute certainty that you have determined causality. And in terms of the classical stats, there's two big categories. There's your parametric statistics and your non-parametric. And the parametric, there's all these assumptions you're supposed to check. So, good to check them. There are many assumptions that are robust to violations, like, do your errors actually have to be more normally distributed or not? A lot of that really depends, in my experience, on the effect size. And if something works and there's a big effect, yeah, you can violate the assumptions and you'll still see the effect. Whereas if there really isn't a lot of there, you can check your assumptions till the cows come home and add all these covariates and do all this tweaking, and it's just not going to make that big of a difference. But it is good to check that. And that's an advantage of the non-parametric statistics used a lot in biology or your machine learning techniques. They tend to either have few to no distributional assumptions about the underlying data. So they're very friendly that way. In a similar fashion, if you're using parametric statistics like a multiple regression and you want to do interaction techniques, you have to specifically define those. Whereas other techniques like neural networks and decision trees, they'll automatically bring in interaction effects and nonlinearities. So I like to be wary of methods effects. Like you only use one technique and you find one particular conclusion. It's good to have 2 or 3 different models to make sure that your findings are robust, because it could be that your data pattern just happens to fit a particular model, whereas having multiple different approaches then makes you more confident that there's a there if you're finding some sort of an outcome or a lack of an effect too, which is often helpful to know. And no matter how good of a job you do in your project, it doesn't mean that your one project is it. There's no one effort that says, okay, I did the one study and that's the end of the question. You got to have replication. You got to have other people test it out. And that's one of the things, going back to the multiple measures project. We did the work at the state level, put our code out there, help train local researchers how to do it so then people could replicate it locally, knowing how we did it, but then also trying it their own way as well with their own techniques, and to help triangulate and ensure that what we were seeing was true, especially because of the implications and consequences on the policy side. You want to make sure there's a ton of replication, lots of different people looking at it. And then finally, it's easy to mistrust predictive models. A lot of people don't understand them. And when you explain, I'm taking this hypothetical set of students, spanning over these variables that may or may not have populated data in it and doing these estimates to predict a future cohort of students that doesn't exist yet, some people might think you're kind of making stuff up. So it's really important to take a lot of time in the presentation side. Ensure that you're grounded so that your tech people feel confident that you're doing the right stuff. And then your non-technical people are welcomed in. You don't want to insult their intelligence. They can learn a lot of stuff. They can understand the concepts of covariates, relatively quickly, if not be able to do it themselves. But making sure you take a lot of time with the presentation of the results so that people understand what you can and cannot infer. What's the limits of inference? What population do these findings apply to, and which populations do they not? What are some threats to validity? Some of my friends tease me that I spend more time on caveats than presenting the results, but it's good for folks to know the real deal. so they have confidence in what you're ultimately indicating. Either it seems like it is working or not working, as most of our work ultimately winds up in some sort of recommendation of keep doing this or don't keep doing that.
Excellent. Thank you. That was a great representation and just response to those three questions. And then we're going to the bonus question. And the bonus question is, last time was what your favorite donut was, and now is what do you prefer, coffee or tea, and which is your favorite? And I mean, which brand or type is your favorite?
I prefer coffee.
Okay.
And the type, it depends. My morning cup of coffee, I like a dark French roast. But for my afternoon cappuccino, I like a nice medium espresso roast.
Excellent. Is there any brand that you'd recommend or coffee house you'd recommend?
I do like the higher quality coffees, and especially if they're shade grown, environmentally friendly, and work with the local workers to make sure they get a cut of the action. You can really taste the lack of exploitation in a good cup of coffee that's consciously sourced. They do taste better, and you feel better about drinking it. Um, we do have a local roaster, Santa Cruz Coffee Roasting Company. I drink that, a fair amount. Part of it's local in the sense it's locally roasted. I mean, we certainly don't grow the coffee here, that's for sure. Not the right kind of climate for that.
That's cool. Well, thank you so much, Terrence, for hanging out today and sharing some insight. I look forward to seeing you again. Have a great one. Thank you.
Yeah, you too. Thanks for having me.